Thank you. It's a great pleasure to be here in front of this diverse audience. There's a personal thing. I was going to speak about the Johnson-Lindenstrauss lemma, and actually both Bill Johnson and Yoram Lindenstrauss were friends of my family. And so this is a picture of my father, Elton Lacey, with Yoram Lindenstrauss, and you can tell by the glasses and the ties that it was just about the time that Bill Johnson and Yoram Lindenstrauss proved their famous lemma. So I'm speaking about one-bit sensing, which Simon just introduced. So this is a sort of more in the compressive sensing framework. This will be a low-tech talk, but I have one important message in it. So so X is a signal, and then the measurements are inner products of X, where theta j is a design parameter. And then the one-bit measurement is you take all of this information that's in the inner product and you throw most of it away. That you only keep the sign of the inner product. So why would you do this? Well, there's actually several different reasons. It's an extreme form of a nonlinear measurement, and there's a very funny technological trade-off that has many sort of interesting consequences. Is that if you reduce the size of a measurement from a physical system, you could actually take many more measurements. So this is an actual movie of a photon bouncing off of a mirror, and a little bit of the photon goes behind. But this is not, I don't know anything about physical chemistry, but just to say that there's an important trade-off between size of a measurement and number of a measurement, which is being exploited in different ways. So the message I have is that when you make this nonlinear measurement of a signal, there's an important underlying change in metrics and an important underlying change in the stochastic processes that govern how these measurements work. So if we think in this slide, we have a vector. Well, second is, as we've already heard, if you take a one-bit measurement, you can't learn the length of the vector, x. So all vectors live on the sphere. And if we have a vector x, it defines an equator. And so if your measurement theta is on this side of the black equator, the dot product is positive. If it's on the other side, the dot product is negative. If I choose a different vector y, I get a different equator, and I have more, but otherwise the story is the same. And the significance of this is you have to ask yourself which measurement vectors theta will distinguish x and y, will tell you that x is not y in the one-bit context. That's exactly the symmetric difference of the hemispheres. So if you select the thetas at random, you need to ask yourself, what is the probability that my one-bit measurement would distinguish x and y? That's simply the probability of that symmetric difference of hemispheres. That's this side. What is that probability? It's geodesic distance. It's a normalized geodesic distance on the sphere, normalization so that North Pole and South Pole would be a distance 1 apart. All right, so the geodesic distance is approximately Euclidean. but it is not. And so to fine analysis of one-bit measurements requires that you accommodate this geodesic distance. All right, so as I've already said, the one-bit map can't recover the magnitude of x. But now we're going to step into making several one-bit measurements. And so if I have a single one-bit measurement, I have a one-bit map that takes the unit sphere into -1 or +1. I'll make several measurements. And we have a map from Sn-1 into the Hamming cube, HM, whose dimension equals the number of measurements. And so on the Hamming cube, of course, we'll use the Hamming metric. We have our sequence of one-bit measurements. A number of them will equal each other. They contribute nothing to the distance between them. And if they differ, that counts 1, and then we normalize. So we have a maximum distance of 1. And so in the one-bit context, if I have some sort of m-dimensional one-bit map, I have a map from the sphere on the left to the Hamming cube on the right, and I have a map from geodesic distance on the left to Hamming distance on the right. And so now I'm recalling the Johnson-Lindenstrauss lemma in the sharpest form that I know of, the result of Dasgupta. And I'm recalling the RIP property, which Simone was just talking about. So you have a finite set N of R capital N. Capital N plays no role in the rest of the statement. And the cardinality of calligraphic N is little n, and epsilon between 0 and 1 is the RIP parameter. Then there's a linear map A that maps R into Rm, so that that should be calligraphic. If I take any 2 points in the calligraphic N, and I compare the distance in the image, it's comparable, distance squared, it's comparable to the origin. So that's Johnson-Lindenstrauss lemma. And M, this Dasgupta bound, is of this nature. So this is a very beautiful fact. It more or less works by choosing a random subspace of this cardinality and then proving that this inequality holds. And this is all done in a beautiful way using the Gaussian random vectors and chi-square distributions. The same statement is true for the one-bit context. In fact, the constants are better, just a little bit better. Okay, so it's the same statement, same typos. Calligraphic N is contained in some sphere. The role of capital N is irrelevant. It has cardinality little n, and delta is the RIP parameter, but remember that the metrics have changed. And there's a one-bit map from this sphere into the Hamming cube, so that if you compute for any pair in calligraphic N, you compute the geodesic distance and you compute the Hamming distance of the images, they're very close. And M need only be 2 log n over delta squared, but I insist that this is the same number as before. In fact, it's a little better. remember that there's square interceded in the previous version of RIP. So so once you take the square into account, it's the same number. So this is a counterintuitive fact. You throw away the information, and in fact, your RIP property is just as good. Well, this is such a striking fact, it demands some, so it's the 1-bit bound is just a bit better, but it's such a striking fact, it needs some explanation. The explanation is just one sentence. If you take a 1-bit measurement under this IID circumstance, and you compare and you say, have I distinguished the two vectors x and y, you're getting a Bernoulli random variable. It's either 0 or 1. Of course, it has a parameter to it, an unknown parameter. Well, the parameter is given by the geodesic distance. So when you sum Bernoullis, they're universal sub-Gaussian. Right? They satisfy each, no matter what the parameter is, they satisfy a sub-Gaussian estimate, and coin tossing is the worst case. And that's the only fact that you need to prove this statement. And in fact, it was done, oh, that's a terrible picture. I didn't realize the resolution was so low. It was done in an REU project last summer. So it literally is at an undergraduate level. And the REU students went on and examined phase transitions in the RIP property for special classes of mappings, where you take a special set of vectors and you map them into the 1-bit Hamming cube, into the Hamming cube. There's a very sharp and narrow phase transition that takes place between not being an RIP and being an RIP. So I think if I'm really, really short, everybody's happy, right? Right. So I emphasize that the fact that you have this 1-bit measurement introduces a nonlinearity, and this changes the underlying metric. And this, in the 1-bit case, it changes the underlying metrics from Euclidean to geodesic. Associated with the compressive sensing literature is a notion of a Gaussian process that sort of governs things. So the fine properties of linear compressive sensing are based on analysis of chi-square processes and a comparison to the usual linear Gaussian process where you take a canonical Gaussian and you just take inner product with x. So the fine properties of 1-bit compressive sensing are related to a geodesic Gaussian process, which I'll describe next. And now I ask you to remember the picture of the sphere. And so if I fix an x, I have the northern hemisphere relative to x. So you draw the equator, and then you take the equator that contains x. That's hx. Now let W be a white noise on the sphere. So it's a measure. A white noise is a measure. And you input a Borel set, and you get back a Gaussian. And the Borel set that you input is the hemisphere. And then the metric, so call that B sub x, and then this is a mean zero Gaussian process. It has a metric, and the metric is a geodesic metric. So so this is the relevant underlying Gaussian process, just a little different from the standard one. So there's a very beautiful notion of a statistical dimension associated to coming from the compressive sensing literature, and there's a corresponding 1-bit notion of statistical dimension. So you take an arbitrary set K inside the sphere, and you want to know its statistical dimension. And so you go to this geodesic, this is the geodesic process, B. You form the soup of this guy, take expectation, and that's the statistical dimension. So it plays the same role as the ordinary statistical dimension in compressive sensing. When you pass to, say, sparse vectors or something like that, you wind up needing different kinds of observations. One of which is that if you look at the sets of hemispheres, this is a collection of sets in the sphere. There's an abstract notion that we know from Vapnik and Chevranankis called VC dimension. And so it makes sense to speak of the VC dimension of the sets of hemispheres. So if I specialize the sets of hemispheres to be those associated with sparse vectors, and I calculate their VC dimension, it's exactly what you want it to be. We know that these kinds of numbers are closely associated with covering numbers. So if K is a subset of the sphere and D is a geodesic distance, and so that should be a delta, I guess, NK delta is the least number of geodesic balls of radius delta needed to cover K. And so I have just 2 more slides left. One of the nice, attractive parts about this 1-bit sensing is that there was a lot of allied notions similar to RIP property that were investigated. This is one. So you have a K as a subset of the sphere, and you consider a set of hyperplanes, or these are equators actually, which are identified with our normal vectors. And so dHxy is the fraction of hyperplanes which separate x and y. And then H is a delta uniform tessellation of K if you have this kind of RIP-like looking property. So you compute the geodesic distance here, and dH is defined up here. And so using these covering numbers, you can prove that that if you have any K at all, so this can be arbitrary, it can be very far from just the sparse vectors, and any delta, if you make a random choice of hyperplanes of at least this many, you'll have a delta uniform tessellation of K with very high probability. So I think this sort of explains my point of view on 1-bit sensing, and I didn't prepare more, and I yield the rest of the time back to the audience.